Let's solve the kind of equilibrium problem that sometimes gives students a tremendous amount of pain. And let me explain what I mean. You're just given an equilibrium constant in a chemical system and told to find the equilibrium concentrations under certain conditions. Let's take a look. This is a problem that we might see in such situations. If 2 moles of nitrogen dioxide gas are put into a 4.00 liter container, calculate the equilibrium concentration of all species. And they say that at this temperature, whatever it is, Kc is equal to 6.0 times 10 to the negative 7th. Sometimes it'll be a Kp and you have to use partial pressures, but in this case you're going to be using the concentration or moles per liter. And the concentration of the nitrogen dioxide in this case must be 2 moles in 4 liters or 0.500 molar. Now we can plug this into a rice table. We've already got the reaction. So the ICE are here and we have no products to start with and 0.500 molar to begin with. And we'll ignore the capital M in our verbal discussion, but try to keep it when it's necessary on the screen. All right. As in thermo, we want all our work to be per mole of reaction. So we're going to find a coefficient of 1, and in this equation the coefficient of 1 is the moles of oxygen gas. That makes it a little easier. So X will be the number of moles of oxygen gas produced. This requires 2 moles of nitrogen dioxide to be consumed, and so that also comes with 2 moles of nitrogen monoxide product as well. The change in this process then is the production of X moles of oxygen and 2X moles of NO and the loss of 2X moles of NO2. So the equilibrium amounts of NO and O2 are thus accounted for. But what's the equilibrium concentration of the nitrogen dioxide? It must be the initial 0.5 molar less the 2X needed to produce the nitrogen monoxide and, of course, the X of the oxygen gas. Because, of course, the coefficient on NO2 is 2, just like it is on the NO. Now, if you're mathematically astute and you look at that first term under E, you can look and see that the quadratic formula problem is looming over our heads because NO2 is squared. But take a look at Kc, and you should always be aware of what Kc means. What does this tell us about the extent of the reaction at equilibrium? If you're with a study group now, you might just kind of pause the video and discuss that. Hopefully you see that Kc tells us that at equilibrium there's still a lot of reactant and not much product. The product over the reactants is a very small number. Kc tells us that at equilibrium X and 2X are very small compared to the initial 0.5 of the reactant. So we're going to assume that 2X is a negligible quantity compared to the initial NO2 concentration. And you should state this in an FRQ in your solution to the problem. Write it out. In this case, 2X is negligible compared to the initial NO2 concentration. And we're going to tentatively remove it from the calculations. And there it goes. Now, the equilibrium numbers look more manageable, and they are. 2X is much less than 0.5. Now, we'll need to come back after we've solved the problem to see if our assumption is okay. So, Kc, of course, is the square of the product NO concentration times the oxygen gas concentration, and that's all divided by the square of the NO2 concentration. All of these numbers are at equilibrium. We plug in what we know from the rice table, and we get 2X, both squared, times X as our numerator, and 0.5 squared as our denominator. which means we've got 4x cubed in the numerator and 0.250, the square of 1/2, in the denominator. And when we put that together, we see that Kc is equal to 16x cubed. Now, that means that x cubed, if we divide both sides by 16, is equal to 0.375 times 10 to the negative 7th. Before we take the cube root of that number with your calculator, let's understand that it really makes sense to simplify here. We can easily take the cube root of a power of 10 if it's divisible by 3. So let's change that exponentiated number and, of course, the number ahead of it. We are going to make the 0.375 100 times bigger. And, of course, we have to make the 10 to the negative 7th 100 times smaller. So we now have a valid relation. X cubed is 37.5 times 10 to the negative 9th. You can take the cubed root of 37.5 with your calculator, and of course you just divide by 3 the exponent on the 10. That means x is 3.35 times 10 to the negative 3rd molar, and 2x is 6.70 times 10 to the negative 3rd molar. Great, we've got a solution for the NO and the O2. Now we have to validate our original assumption about the equilibrium concentration of the NO2 being very, very close to its initial concentration. So let's plug in the numbers and see. Using our 5% rule, this may be a new thing to you, but it says, and this is the AP's words, if our variation from perfection is less than 5%, we can rely on our original assumption. Well, the value of 2x is approximately 0.007. That would reduce our original NO2 concentration to 0.493 molar at equilibrium. The change is less than 5%, so our assumption meets the test, and we could ignore the need for a quadratic formula solution. We now have our solution. The nitrogen dioxide equilibrium is 0.493 molar. The nitrogen monoxide is 6.70 times 10 to the negative 3rd molar, and the oxygen concentration is 3.35 times 10 to the negative 3rd molar.